Welcome to The Explainer. Today, we're zooming way in to look at the actual anatomy of a nuclear split. We hear about nuclear power all the time in the macro sense, massive cooling towers and huge energy grids. But the real magic, that happens on a subatomic level, guided by some truly wild rules of quantum physics. Understanding these rules is the absolute key to grasping how we power entire cities and honestly, why nuclear waste is such a tough puzzle to solve.
Here's our roadmap for today. We'll be hitting the nuclear ingredients, breeding new fuels, the splitting point, the asymmetry mystery, and wrapping up with chasing magic numbers.
All right, let's kick things off with Section 1, the nuclear ingredients, and the massive resource challenge we face every single day.
Okay, I want you to focus on this shockingly tiny number, 0.7%. When we're talking about a nuclear reactor, you can't just toss in any random material and expect to generate power. You absolutely need fissile material. And the only naturally occurring fissile nuclide on Earth is uranium-235. But here's the wild part. If you dig up a random chunk of natural uranium, a mere 0.7% of it is actually that precious, highly usable U-235.
And that perfectly illustrates a massive scarcity problem for us. A whopping 99.3% of natural uranium is just non-fissile U-238. This crazy imbalance is the exact reason why the world has to build those massive, ultra-complex uranium enrichment facilities. It forces the whole industry to handle that tiny sliver of usable fuel with extreme care. It's a huge economic and scientific responsibility to maximize such a rare natural resource.
Which brings us right to Section 2. Breeding new fuels. We're talking literal subatomic alchemy here.
So since nature didn't give us nearly enough fuel, we actually have to create our own. We do this by taking those incredibly abundant but otherwise unhelpful fertile materials, like all that U-238 we just talked about, and we forcefully breed them into fissile materials right inside the reactor. It's honestly like turning lead into gold, but it's completely real, and it happens through a process called neutron capture.
The transmutation process actually happens in 3 incredible steps. First, a totally non-fissile U-238 atom absorbs a stray neutron just floating around the reactor. Boom! Suddenly, it becomes U-239, which is super unstable. Over about 24 minutes, it undergoes beta decay to become Neptunium-239. Give it a couple more days, and it decays again. The final result? It essentially shapeshifts into a brand new, highly usable, man-made fuel, Plutonium-239. We are literally breeding our own fuel on the fly as the reactor runs. How cool is that?
Now that we've got our fuel sorted out, let's move to Section 3, the splitting point, the main event.
So when the atom finally breaks, it is an incredibly violent event. It's usually a binary split, meaning it snaps into 2 distinct pieces. We call those fission fragments. Now these 2 fragments are flying apart incredibly fast, and they're carrying about 80% of the total fission energy as kinetic energy. On top of that, these new fragments are highly excited and highly unstable. Because of this, they're going to desperately try to shed that excess energy through different modes of radioactive decay, like spitting out alpha, beta, or gamma radiation. And honestly, this desperate shedding of energy is exactly what creates the dangerous radioactive waste we're always hearing about in the news.
But here's where the physics gets delightfully weird. Section 4, the asymmetry mystery, a truly strange paradox. I really want you to think about this question for a second. Why doesn't the nucleus split evenly down the middle? If you picture a water balloon or a perfectly symmetrical sphere of atomic material, and you add just enough energy to make it pop, intuitively, you'd totally expect it to break into 2 equal halves, right? A clean 50-50 split just makes mechanical sense. But welcome to the quantum world, where intuition goes right out the window.
There is a fascinating phenomenon called the M-curve. If the split was perfectly symmetrical, we'd see a huge peak of fission fragments right in the middle, right around a mass number of 117 or 118 for uranium. But instead, we get a massive trough. The data completely proves that symmetric splits are incredibly rare. In fact, lopsided, asymmetric splits are favored by a factor of over 500. So the atom almost always snaps into one distinctly heavier chunk and one lighter chunk. No 50-50 split here.
To figure out why it's so lopsided, we have to look at Section 5, Chasing Magic Numbers, and something called the shell model. It turns out the nucleus isn't just some random soup of particles. According to the shell model, protons and neutrons really just want to snuggle into highly stable, closed energy shells. Think of it kind of like a perfectly packed moving box where absolutely nothing rattles around inside. And these perfectly closed shells correspond to very specific quantities of particles, which physicists literally call magic numbers. When an atom is splitting, the resulting fragments actively, almost aggressively, seek out these magic number configurations so they can achieve maximum stability.
During this crazy subatomic dance right on the eve of fission, the material is desperately trying to organize itself. One side, the heavier fragment, is greedily seeking out a magic proton number of 50 and a magic neutron number of 80, simply because that specific combo is incredibly stable. But for one side to grab that perfect magic setup, it basically has to hoard the mass, leaving whatever scraps are left over for the lighter fragment. So it's the heavy fragment's absolute demand for stability that forces the split to be totally unequal.
But getting to those magic numbers comes with a pretty dangerous side effect. The original, massive parent atom, the actinide, naturally needs a really high ratio of neutrons to protons just to hold itself together. But smaller atoms, like our brand new fission fragments, naturally need a much lower ratio to stay stable. The catch is, during the split, the massive parent atom's original stockpile of neutrons gets shared between the two smaller kids. This forces our newly born atoms to inherit a dangerously high neutron-to-proton ratio. They end up overwhelmingly, stubbornly neutron-rich.
So how do they fix it? Well, because they're so neutron-rich, these tiny fragments can't just exist peacefully. They have to frantically decay by emitting beta particles. In beta decay, a neutron effectively turns into a proton, which gradually lowers that dangerous ratio. They'll just keep firing off beta radiation, transforming step by step until they finally hit the right balance and find ultimate peace and stability. And this relentless beta decay process? That can take thousands of years, which is exactly why spent nuclear fuel has to be stored so safely for generations.
From dealing with the scarcity of our natural fuels, to literally breeding plutonium, all the way down to atoms snapping asymmetrically just to find their magic numbers, it's a beautiful, chaotic pursuit of stability. Every single millisecond inside a nuclear reactor is defined by this invisible dance, which leaves us wondering, as we keep pushing the boundaries of nuclear science, what other hidden subatomic dramas are playing out right now inside these reactor cores, just waiting to be explained? Thanks for diving into this explainer with me, and keep questioning the mechanics of our universe.